The 75% demand factor for appliance loads in single or multi-family units, as per the 2023 National Electrical Code, or NEC, is specifically addressed in Section 230.53. It's crucial to understand the stipulations within this section to correctly apply the demand factor and ensure accurate load calculations. The demand factor allows for a reduction in the total calculated load, based on the assumption that not all appliances will be operating simultaneously at their maximum rated power. However, this reduction is only permissible under certain conditions. Firstly, the dwelling unit in question, whether it's a single-family home or a unit within a multi-family building, must have 4 or more permanently installed appliances. These appliances must be fastened in place, meaning they are intended to be fixed in location and not easily moved. Examples include dishwashers, garbage disposals, water heaters, and built-in ovens. Portable appliances, such as toasters or blenders, do not qualify for this demand factor. Secondly, each of the appliances must be rated at not more than 1200 watts. This limitation is important because the demand factor is predicated on the assumption that these smaller appliances will not collectively draw their maximum power at the same time. Larger appliances with higher wattage ratings are assumed to have a more significant and predictable impact on the overall load. In a multi-family dwelling, the demand factor applies to each individual unit separately. This means that each unit within the building must independently meet the criteria of having 4 or more permanently installed appliances, each rated at 1200 watts or less. The total number of appliances across all units in a building is not the determining factor. For example, consider a 10-unit multi-family dwelling. If each unit has only 3 fastened-in-place appliances, even if the total number of such appliances across all 10 units is 30, the demand factor does not apply to any of the units. Each individual unit must meet the minimum requirement of 4 qualifying appliances for the demand factor to be applicable. Understanding this distinction is crucial for accurately calculating the service load for multi-family dwellings and ensuring compliance with the NEC. Failing to properly apply the demand factor can lead to undersized service equipment, which can result in overloading and potential safety hazards. Conversely, overestimating the load can lead to unnecessary expense and inefficiency. To further illustrate the application of this rule, consider a scenario where a 4-unit apartment building is being wired. Firstly, imagine each unit contains a permanently installed dishwasher rated at 900 watts, a garbage disposal rated at 500 watts, a water heater rated at 1000 watts, and a built-in microwave rated at 800 watts. Because each unit contains 4 or more fastened-in-place appliances rated at less than 1200 watts each, the 75% demand factor can be applied to the total appliance load of each unit. Secondly, consider a scenario where each unit contains only 3 appliances, a dishwasher, a garbage disposal, and a water heater. In this case, the demand factor cannot be applied and the full load of all 3 appliances must be used in the service calculation. Thirdly, if one of the appliances in a unit exceeds 1200 watts, such as a large electric range rated at 6000 watts, the demand factor cannot be applied to the other appliances in the unit, even if they meet the other criteria. The presence of a single appliance exceeding the wattage limit disqualifies the entire unit from the demand factor. Calculating the appliance load with a 75% demand factor involves the following steps. 1. Identify all permanently installed appliances in the dwelling unit that are fastened in place and rated at 1200 watts or less. 2. Sum the wattage ratings of all qualifying appliances. 3. Multiply the total wattage by 0.75 to obtain the demand load. For example, if a unit has 4 appliances with a total wattage of 3000 watts, the demand load would be 3000 watts multiplied by 0.75, which equals 2250 watts. This demand load is then used in the overall service calculation for the building. It's important to consult the specific edition of the NEC adopted by the local jurisdiction, as code requirements can vary. Additionally, local amendments may further modify or clarify the requirements for appliance load demand factors. Consulting with a qualified electrical inspector or engineer is always recommended to ensure compliance with all applicable codes and regulations. Other sections of the NEC may also be relevant to appliance load calculations, such as those addressing general lighting loads, receptacle loads, and motor loads. A comprehensive understanding of these requirements is essential for accurate and safe electrical system design. Furthermore, it's important to note that the 75% demand factor is just one of several demand factors that may be applied to different types of loads in a dwelling unit. The NEC provides demand factors for lighting loads, heating and air conditioning loads, and other types of equipment. Each demand factor is based on specific assumptions about the diversity of the load and the likelihood of simultaneous operation. When calculating the total service load for a building, it's necessary to carefully consider all applicable demand factors and apply them correctly. Failing to do so can lead to inaccurate load calculations and potential problems with the electrical system. In summary, the 75% demand factor for appliance loads in single or multi-family units is a valuable tool for reducing the calculated service load and optimizing the electrical system design. However, it's crucial to understand the specific conditions under which the demand factor can be applied and to follow the NEC requirements carefully. By doing so, it's possible to ensure compliance with the code and provide a safe and reliable electrical system for the building occupants. Remember to always refer to the latest edition of the NEC and consult with qualified professionals to ensure accurate and safe electrical installations. For those preparing for electrical licensing exams, a thorough understanding of the appliance load demand factor and other NEC requirements is essential for success. Practice applying the demand factor to various scenarios and familiarize yourself with the relevant code sections. With diligent study and preparation, passing the exam and obtaining your electrical license is achievable. Let's delve deeper into specific appliance examples to solidify understanding. Firstly, consider a typical apartment unit equipped with a dishwasher, a waste disposal unit, a refrigerator, and a microwave oven. Assuming the dishwasher is rated at 900 watts, the waste disposal unit at 400 watts, the refrigerator's compressor at 200 watts, and the microwave oven at 800 watts, all these appliances meet the fastened in place and wattage requirements. The total connected load for these appliances is 2300 watts. Applying a 75% demand factor results in a demand load of 1725 watts. Secondly, imagine a scenario where the same unit has a large, permanently installed electric range rated at 6000 watts instead of the microwave. In this case, despite the other appliances still meeting the requirements, the presence of the electric range exceeding 1200 watts disqualifies the entire appliance load from the 75% demand factor. The full 6000 watts for the range must be factored into the service calculation along with the full load of the other appliances. Thirdly, let's consider a unit with only 3 qualifying appliances: a dishwasher, a waste disposal unit, and a refrigerator. Even if their combined wattage is relatively high, for example, totaling 1500 watts, the absence of a fourth appliance means the 75% demand factor cannot be applied. The full 1500 watts must be used in the service calculation. It's also important to consider the implications of permanently connected appliances that may not be in constant use. For instance, a permanently installed attic fan or a central vacuum system might qualify as fastened-in-place appliances, but their usage patterns are typically intermittent. While they contribute to the total number of appliances, their contribution to the overall demand load might be minimal due to their infrequent operation. Code enforcement officials and electrical inspectors often scrutinize appliance load calculations to ensure compliance and safety. They may require documentation such as appliance nameplate ratings and installation details to verify that the demand factor is being applied correctly. Therefore, it's crucial to maintain accurate records and be prepared to justify the load calculations if requested. In older buildings undergoing renovations or upgrades, the appliance load may need to be re-evaluated to determine if the existing service is adequate. If new appliances are being added or existing appliances are being replaced with higher wattage models, the service capacity may need to be increased to accommodate the increased load. This is particularly important in multi-family dwellings where individual units may be undergoing upgrades independently. Communication and coordination between the building owner, the electrical contractor, and the local building department are essential to ensure that all electrical work is performed safely and in compliance with the code. In addition to the NEC, other standards and regulations may also apply to appliance installations. For example, energy efficiency standards may dictate the types of appliances that can be installed or the minimum energy performance requirements. These standards can impact the appliance load and the overall energy consumption of the building. Staying informed about the latest energy efficiency standards and incorporating them into the electrical design is an important aspect of responsible electrical engineering. Furthermore, advances in appliance technology are constantly changing the landscape of appliance loads. Smart appliances with energy-saving features and variable speed motors are becoming increasingly common. These appliances can reduce energy consumption and peak demand, potentially impacting the applicability of demand factors. As appliance technology evolves, it's important to stay up to date on the latest trends and their implications for electrical load calculations. The NEC is regularly updated to reflect these changes and to provide guidance on the safe and effective installation of new technologies. Let's discuss the implications for electrical panel sizing. Accurately calculating the appliance load, with or without the demand factor, directly impacts the required size of the electrical panel and the service entrance conductors. If the appliance load is underestimated, the panel may be undersized, leading to potential overloading and tripping of circuit breakers. This can cause inconvenience for the occupants and, in severe cases, pose a safety hazard. Conversely, if the appliance load is overestimated, the panel may be oversized, resulting in unnecessary expense and wasted space. Therefore, it's crucial to perform a thorough and accurate load calculation to determine the appropriate panel size. The NEC provides guidelines for calculating the panel size based on the total connected load and the applicable demand factors. These guidelines take into account the diversity of the load and the potential for simultaneous operation of different appliances. When selecting a panel, it's important to consider not only the current load but also the potential for future expansion. It's generally advisable to choose a panel with some spare capacity to accommodate future appliances or upgrades. This can save time and expense in the long run if the electrical needs of the building increase. The service entrance conductors, which connect the electrical panel to the utilities transformer, must also be sized appropriately to handle the calculated load. The NEC provides tables for determining the ampacity of conductors based on their size, material, and insulation type. It's crucial to select conductors with sufficient ampacity to carry the expected load without overheating. Overheating conductors can lead to insulation breakdown, short circuits, and fires. Therefore, conductor sizing is a critical aspect of electrical safety. In addition to conductor ampacity, it's also important to consider voltage drop. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause appliances to operate inefficiently or malfunction. The NEC provides guidelines for limiting voltage drop to ensure proper appliance operation. To minimize voltage drop, it's generally advisable to use larger conductors or to shorten the length of the circuit. The use of aluminum conductors can also help reduce voltage drop compared to copper conductors of the same size. However, aluminum conductors require special terminations to prevent corrosion and ensure reliable connections. Finally, let's touch upon the importance of proper grounding and bonding. Grounding and bonding are essential for electrical safety and for protecting against electric shock. The grounding system provides a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices such as circuit breakers to trip and to energize the circuit. Bonding ensures that all metallic parts of the electrical system are electrically connected, preventing voltage differences that could cause electric shock. The NEC provides detailed requirements for grounding and bonding, including the size and type of grounding conductors, the location of grounding electrodes, and the methods for bonding metallic parts. It's crucial to follow these requirements carefully to ensure a safe and reliable electrical system. In summary, a 75% demand factor for appliance loads in single or multifamily units is a valuable tool for optimizing electrical system design, but it must be applied correctly and in accordance with the NEC requirements. A thorough understanding of the code, careful load calculations, and proper grounding and bonding are essential for ensuring a safe and reliable electrical system.